This video is for class 9 physics, and today we are discussing determination of relative density of a solid substance by Archimedes principle. Right, we have discussed about the relative density in the previous video. Right, now from that discussion we all know that the relative density is equal to the mass of the body by the mass of water of volume equal to that of the body. We had discussed till here, if you remember, that was mass of the substance by the mass of the water, provided they are of same volume. Now if I want to use the Archimedes principle in this particular formula, right, to make our work easy, using Archimedes principle, the mass of water of volume equal to that of the body is obtained by finding the mass of water displaced by that body when it is completely immersed in water, since a body when immersed in water displaces water equal to its own volume. Now this formula here, okay, of relative density, which says that mass of the substance by the mass of the water of equal volume. So if we immerse the substance whose relative density is to be determined inside water, right, now if I am putting the substance, what will happen is the water will get displaced, right, isn't it? So this displaced water volume will be equal to the volume of the solid, right? Volume of the water displaced will be equal to the volume of the solid. Yes, now using this concept here, right, which comes from the Archimedes principle, okay, a lot more comes from the Archimedes principle in fact. So using this concept, when the object is fully immersed in the water, right, so to use Archimedes principle, the only condition is that the object whose the relative density needs to be determined needs to be completely immersed in the water. Right, now then if it is completely immersed, the formula of the relative density will be mass of the body upon the mass of water displaced by the body, because now the volumes remain same. So if I go further, I can write the mass of the body as weight of the body by multiplying g on both the sides. Both the sides means like the denominator and the numerator. Now the mass of the body becomes the weight of the body, and the weight of the mass of the water displaced will become the weight of the water displaced by the body. I hope you have understood till here. Now this weight of the water displaced by the body sounds familiar to me, right? It is upthrust, right? This was upthrust. Now upthrust has a formula, or it has another form, which is loss in weight of the body in water or upthrust. Right, now upthrust formula, as you all know, is weight of the body in air minus weight of the body in water. Right, now simply I can find the relative density by finding the weight of the body in air and finding the weight of the body in water. Let the weight of the body in air be W1, let the weight of the body in water be W2, then my formula will be W1 upon W1 minus W2. Right, so here there is no need to find the volume at all. Okay, so we get this form of relative density, W1 upon W1 minus W2, where W1 is the weight of the substance in air, W2 is the weight of the substance in the water. Right, sorry, this is in air, this is in water. Okay, so let us discuss this in detail now. Okay, so now we shall describe the procedure to determine the relative density of a solid in two cases: when the solid is denser than the water, that is and it is insoluble, that means it should immerse inside the water, and then when the solid is denser than water but it is soluble. Okay, so let us try to understand these two conditions here with a simple experiment, right, or you can directly relate it also. Okay, Relative density of a solid denser than water and insoluble in it, that means it does not dissolve. Okay, like stone. Procedure: suspend the piece of the given solid with the thread from the hook of the left span of the physical balance and find its weight W1. In fact, you can use spring balance also. It just to find the weight of the solid in air, which is W1. This can have any number. Okay. Next, number 2. Now place a wooden bridge over the left span of the balance and place a beaker nearly 2/3 filled with water so that the water does not spill when the solid is immersed on the bridge. Take care that the bridge and the beaker do not touch the pan of the balance, because that will give us the faulty reading. Okay. Number 3, immerse the solid completely in water such that it does not touch the walls of the bottom of the beaker and find the weight W2 of the solid. Okay, to find the weight W2 of the solid. So this can be done with the help of spring balance also. It will be much easier, right? Now after knowing the values of W1 and W2, okay, let the weight of the solid in air be W1, let the weight of the solid in water be W2. Okay, so in that case I can find the relative density by putting the formula, or by using the formula RD equals W1 upon W1 minus W2, right? We can find the relative density using this particular formula. So loss in weight of the solid when immersed in water is W1 minus W2. So the relative density should be equal to the weight of the solid in air upon the loss in weight of solid in water. So we shall get this formula here, right? So I hope you have understood this. Now we can go to the second condition where the solid dissolves, like for example a cube of sugar. When you are putting inside water, it will dissolve. Now what will happen? If it dissolves, I cannot take out the weight. So how to go about that problem? So for that, the procedure will be, if a solid is soluble in water, instead of water we take a liquid of known relative density. Okay, known relative density, this is very important, in which a solid is insoluble and sinks in that solid. Then the process described above is repeated. Now the relative density will be equal to the weight of the solid in air upon the loss in weight, that is W1 minus W2, right? Then we multiply whatever the answer we get after calculating with the relative density of that given liquid. Okay, so I hope you have understood this also. Now coming to the last topic from this section, determination of the relative density of a liquid by Archimedes principle. In the previous cases we were determining the relative density of a solid. Now we are trying to calculate the, or determine the relative density of a liquid. By definition, the relative density of a liquid is given as the weight of the given volume of the liquid upon the weight of the same volume of water. Now this was from the formula, right? ms upon mw, mass of the substance, upon the mass of the water of same volume. So when we multiply with g on the both the sides, we shall get the weight here. I hope you have understood this. Now by Archimedes principle, if a solid is immersed in a liquid or water, it displaces the liquid or water equal to its own volume. That means we are taking one solid, extra solid, whose relative densities need not be known, right? We are just using the solid to find the relative density of the liquid. So therefore the above equation will take the form: relative density will be equal to the weight of the liquid displaced by the body upon the weight of the liquid displaced by the weight of the water displaced by the the weight of the water displaced by the same body. So here since the volume will be same, so therefore now we have a valid formula for the relative density of a liquid. Now going further, so the weight of the body in air minus the weight of the body in the liquid shall give me the weight of the liquid displaced by the solid, right? Upon the weight of the body in air minus the weight of the body in water shall give me the weight of the water displaced by the object or the body, right, which is immersed. In both the cases the body immersed should be same. Thus, to find the relative density of a liquid using Archimedes principle, we take a body which is heavier than both the given liquid and the water, and also insoluble in both, right? The body is first weighed in air, then in liquid, then in water, right? So we have three weights here, W1, W2 and W3. So if the weight of the body in air is W1 gram force, if in liquid it is W2 gram force, and in water it is W3 gram force, then from the equation 5.14, this one here, right, this one here, we can write it as relative density of liquid will be equal to W1 minus W2 upon W1 minus W3. So we are doing till here. Thank you so much.